All right, so got your homeworks here. I've gone through the data collection stuff that you submitted, and frankly, I was really pleased. Some of these figures did a great job of identifying what data is still missing, and I've just about 5 minutes ago got an email response from Huntington Sanitary Board just saying that they're on it. They're going to start gathering the data that we need. So I don't know. They probably won't be able to tell us every single pipe what we need, but they should give us a better idea. Chris, here. Was there an extra copy of the notes? Was there an extra copy of the notes? No? Okay. Let's finish up precipitation. There is a series of interpolated maps that were generated a number of years ago called Hydro 35. And you can see figures like this in just about any hydrology textbook that come up with sort of typical rainfall amounts. And you can see here from the legend, this is a 2-year storm, 60-minute precipitation duration. And so this is a depth, a precipitation depth that you could expect to see. And so there would be a map like this for a 2-year 60-minute. There would be a map for a 100-year 60-minute. And then they wouldn't have maps for a 5, 10, 25, 50. What you'd do is you just use various statistical interpolations. So you'd look up on the map for the area you're interested in. What is the 2-year 60? You'd find the depth. You'd find the 100-year 60, find the depth, and then interpolate between them. And that's sort of the old way that IDF curves would be generated for a location of interest. And you've already seen the precipitation frequency data server. It's still up last time I checked. But if that website goes down, this is how you could generate an IDF table. You'd look up the values off of a map, and then you can do interpolations. If you know the 10-minute storm, for example, you can find, you can find the 10-minute storm by interpolating from the 5 and the 15. It's a sort of weighted average. Likewise, you can find the 30-minute storm by having a weighted average of the 15 and the 60. And then you can interpolate for different return periods. Now this is, what I've just shown on screen here is a way to find unknown storm durations. And it's a little confusing because both return period and duration have units of time. But they have very different temporal scale. When we're talking about 10-minute and 2 years, you wouldn't ask, so which is the duration and which is the return period, right? Because the storm isn't going to last 2 years, and the return period wouldn't be 10 minutes. It's obvious which is the return period and which is the duration, but sometimes it's a little confusing anyways. This is how you'd interpolate between return periods. And so on the previous slide, we looked up and saw that there was a map for the 2-year and a map for a 100-year, and then everything else in between you can just interpolate using these A coefficients and B coefficients. They would go into that equation. And so really, if all you had was the 5, 15, and 60 for the 2 and the 100-year storm, so those 6 values, then you could fill out an entire IDF curve for every return period and every duration between 5 minutes and an hour. And so that would be, for the most part, you could get everything you needed from 6 values. Or, even better, just use the precipitation frequency data server. And part of the reason why the precipitation data frequency server is better, as we'll talk about in just a minute, is that those old Hydro 35 maps were generated back when we had less precipitation data than we've got now. So we've got more data, and the statistical estimates have improved. Just to reiterate the concept of how you can get a volume by a depth. Sometimes it's very confusing to students initially to convert an inch of rainfall into a rainfall volume. And remember that it has to do with the area over which a rainfall depth falls, and that's how you turn it into a volume, is you'll have a certain depth of precipitation, and so that if you have a rainfall intensity and want to find the rainfall amount, you just multiply it by the duration of the storm. And we've talked about return period or recurrence interval before. These concepts are sort of old hat since we rearranged the curriculum to start talking about urban precipitation at the beginning of the course. So here's what I was talking about just a little bit ago, that the Precipitation Frequency Data Server is based on data that's called NOAA 14. The NOAA Atlas NOAA Atlas 14 Volume 2 Version 3. I think that's probably the most recent data set. And Hydro 35 was related to something called Technical Paper 40. That's where the data was published. And what this slide shows is the difference in precipitation amount between the old data and the new data. When they had additional years of precipitation, they had new gauges to put into their spatial averaging. What they came up with is that in some areas there's actually more precipitation than previously estimated, and in others there's less. And so the red zones here, you can see that that the NOAA Atlas 14 is saying that there's less precipitation than there was with TP 40. So if NOAA Atlas 14 is greater, then you'd have in the green range here. So in northeastern Ohio, they're having more precipitation than was originally anticipated. And much in West Virginia, there's less than originally thought. This gives you an idea of stations that they used for daily data. And also, here's a representation of the number of stations that have a certain amount of data. So 50% of these stations had about 55 years of data. 100% of these stations that were included had at least 30 years of data. There's a lot more daily rainfall stations than that. It's just that the other ones that aren't shown have less than 30 years of data, and so they weren't included in the analysis. There was only 10 of the stations in this entire vicinity that had 100 years of data. And so not very many of these stations have been operated for 100 years or longer. And that gives you an idea of part of the reason why the NOAA Atlas 14 is an improvement over Hydro 35 estimates is just, in the intervening years, a greater number of the stations had the minimum amount of 30 years of data that could be included in their analysis. There's also, as you know from an IDF table, it's not just daily data. The IDF table includes precipitation intensities of an hour, 15 minutes, down to 5 minutes. And so there's not very many stations that have data that's being gathered on an hourly or on a n-minute basis. And so if there's a station that's gathering data every hour or every several minutes, you'll notice that here in the tri-state area, there are two, one at the airport and one in Huntington. Here's one in Charleston, that's the Yeager Airport Station. A lot of these in red are airports. Here's the Akron-Canton Airport, the Cleveland Airport, Columbus, Cincinnati, and so on. It's these stations that are responsible for generating the really short duration precipitation intensities. And you can see that the number of stations that have a lot of data are even lower. Why do you suppose that is? That we had at least 10 stations that had 100 years of data, but now there's no stations that have 100 years of data. Why do you think that fewer stations have a longer record history compared to here when we're talking about the daily data? We had, for 50 years of data, about 70% of all of those had 50 years of data when it came to the daily data. But when it comes to hourly data, if we want to know, like 70% would only have about 30 years of data. Yeah. Just think about back before there was electronic equipment available. In order to have hourly data, what somebody would have to do is take a physical measurement and write it down in a logbook somewhere. And so maybe there would be someone on hand to do that at a big international airport. But at the rest of the stations that are automated these days, because direct human involvement isn't justified, it would be prohibitively expensive to have hourly measurements or measurements every 5 minutes. Whereas now, since we can use electronic measurements and digital recording and transmittal of the data, it's a little bit easier to have a good spatial scale and a higher resolution view of what the rainfall is doing on the minute-by-minute basis. Okay. Here's a table of precipitation data for the Huntington Airport. And so the question I wanted to ask you is this a table of amount or intensity? Can you tell just by looking? All right. Why do you say it's amount rather than intensity? What's the clue? Well, we don't, okay, all right, inches per hour. But what if I should obscure this part of it. I should obscure that part of it so that you can't tell from the units, just from the numbers themselves without looking at the units. Nick?
It'd be smaller as time goes up.
Perfect, yeah. Because a storm that has a short duration, remember, should have a higher intensity. And so what we're seeing is we know this is depth or amount rather than intensity, number one because of the units. But also, just from the numbers themselves, a 5-minute storm compared to a 10-minute storm. The 5-minute storm should have the higher intensity, but of course the 10-minute storm is going to have the greater depth. Even though the intensity is decreasing, the duration of the storm is double, and so the overall precipitation depth is greater. So that's a thing that, because the precipitation frequency data server will allow you to toggle back and forth between depth and intensity. Sometimes at first glance it may not be in the format that you need it in, and so that is just a way to always remind yourself which is which. And so in this case you can circle this is amount or depth rather than intensity. All right, now we're going to be moving on into infiltration. It's chapter 6 in the book. And as always, I'll warmly encourage you to get your money's worth by reading the textbook. This is a really great book for explaining the fundamentals. Not so good for application, but we can fill in the gaps. It's the fundamentals that this book really shines on. And infiltration, if we go to the most basic level, is all about how soil and water interact. And this diagram illustrates when particles aggregate together, the difference between a group of clay particles at the top and a group of sand particles at the bottom. Clay particles are thin sheets of soil grains, and they are bound together by electrostatic forces. Soil particles have negative charges all over them. The clay particles do, and that's why when we look at the Ohio River, for example, the water is brown. And even if you take a sample of that river and you set it in a pail of water, some of it will settle to the bottom, some of the sediments will settle to the bottom, but for the most part it'll continue to stay brown because those very small clay particles each have a negative charge, and they repel one another when they're suspended in water. When the clay particles are in a soil, the water is very tightly bound to the surface of the clay. And we'll look at some graphs that show soil water pressure, and clay has a very high soil water pressure because of the strong attraction between water and the surface of clay particles. In the case of sand, you can see there's a wide distribution in the particles of sand in this diagram. The water is bound to the surface of the sand, but because the particles are larger, there's less of a charge per unit volume. A really high surface area is going to increase the amount of charge per volume of soil. But a lower surface area, you can see that if you were going to draw a box around 1 millimeter by 1 millimeter cube, there's going to be a lot of that volume taken up by the sand grains themselves rather than just a really high specific surface area. So that's one thing to point out, is that the specific surface area, or the area per unit volume, is much lower for sand than it is for clay. And that's partly to explain some of the behavior and phenomena that we'll talk about today. And the other thing is you can see that in a really wide distribution of sand grain particles, tiny little particles fill in the gaps. And there's in fact these really microscopic ones here that would be very small fines. This might be a silt rather than actual sand particles. And because of the packing like that, it forms little voids, very small voids, and the interconnected voids lead to the capillary effect that we talked about in fluid mechanics several semesters. I guess it was last year this time we were talking about the capillary effect, and that's how in a glass tube water will rise up above the free surface of the container that a glass tube would be immersed in. If you have a container of water and you put in a small diameter glass tube, the capillary effect will actually draw the water up in the glass tube in order to maximize contact between the water and the actual surface of the glass tube. So here in a column of sand, if you have a thick layer of sand, then water is saturating part of that, fully filling all of the voids. Then these small interconnected voids here will allow water to rise up above the fully saturated zone. And there are a couple of diagrams we'll move to here in a second that show that. All right, well, consider the soil texture triangle. Have you seen anything like this before in soil mechanics? Some people say yes, some people say no. Soil mechanics was my worst class when I was an undergrad. I'm sure that my professor showed this to me, but I was probably dozing at the time. This was a professor who gave us lectures totally in the dark after lunch. It was a warm room, and he didn't seem to mind if anybody slept, and so lots of us did. I should have paid better attention. I should have, I don't know, had coffee or something before class. So we're going to work through an example here that illustrates how to classify soils into different categories. And the reason why it's important is that different categories of soil have typical soil characteristics that you'll use to estimate infiltration rate. Infiltration rate essentially is when it rains, how much water can be absorbed into the soil. We've been talking about precipitation rate, like there may be a storm that's 3 inches per hour. What we're working towards in this section on infiltration is how many inches per hour can penetrate into the soil. If it's 3 inches per hour, then that's great. We won't have any runoff. But if it's less than 3 inches per hour, and we're getting 3 inches per hour of rainfall, then there's going to be an excess of precipitation that has to flow over the road, over the land. And so that's sort of where we're headed. But one of the important things we have to be able to do is classify soils. Now, here is how you classify soil types by their particle size, and clay, silt, sand, and gravel. And let's classify a soil that in the lab with the sieve analysis, they did a test and found out that of the soil that's there, 25% is greater than 2 millimeters, 40% is in the sand range. So we know sand is between 0.05 millimeters and 2 millimeters. 33% is in the silt range, and then 2% was clay. In order to use this triangle, you'll notice, first of all, that it's got an axis that has sand, and it's got an axis that says clay and silt, but there isn't a gravel axis. And so even though some of your soil classification may be gravel, what we have to do is exclude the gravel amount. And so we're going to want to have another column here that is, what is the percent distribution of the soil if you exclude everything that's greater than 2 millimeters. And so 40, 33, and 2 is the entire sort of modified soil distribution. And so what would be the percentages for sand, silt, and clay? All right, so 40, 33, and 2, that's going to be 75, right? So sand is 40 divided by 75. Silt is 33 divided by 75. Clay is 2 divided by 75. And so what is the percentages of those? 53.3, 44. All right. So what we can do now that we've excluded the gravel is we can say we've got 33.3% sand, and so, I'm sorry, 53.3. So here's sand axis 53. So we're on this axis, and we're going to be going that way until we stop at the percentage of silt. So 44% silt. And you can see that silt goes at that axis. And so here's 53% sand, 44% silt, and then that corresponds to a clay percentage. If we go over with the clay would follow here, and it matches up with the approximately 3% that we'd expect for the clay. Now the angles I know can be a little bit confusing, and especially these other lines here are the division between different categories, and so don't accidentally follow like one of these thinking that it's having to do with the clay line. The clay is horizontal. The clay lines are horizontal. The sand lines are at this axis, and then the silt lines are at that axis. And so you can see the dot there has to do with this particular soil, and so this would be a sandy loam soil because it's within the boundaries of what's classified as sandy loam. And the reason why that's relevant, again, is that sandy loam has certain characteristics we can use in calculating and estimating the infiltration rate. There are a couple of models. We're going to learn 2 models this semester for predicting the infiltration rate. And they're just equations that you can solve by hand or with Excel. We won't be using like a full-blown a separate computer program to apply those models, although those models are built into a couple of computerized hydrologic models. They can be solved just pencil and paper. Any questions on this example of how you can classify a soil according to its category? Soil texture. All right. So if you have a certain soil texture, these are the range of properties. In this example, we had a sandy loam soil. And so if we go to the next slide and we find out where is the sandy loam, here's a sandy loam, and we'd expect a wilting point of approximately 0.06. We'll talk about what wilting point is. The field capacity, this is the range of moisture conditions in the field that would be expected. The drainage by gravity, and then the porosity, the range of porosities, and that's the ratio of void spaces to the complete, to the total overall volume of the soil, the porosity. One of the most important things that governs how quickly a soil can infiltrate moisture when there's precipitation is the tension in the soil water pressure. And this figure is showing for the degree of saturation how much tension there is. This is log 10 of the soil water pressure, and the symbol for that is psi, like the Korean singer Psy. But what you can see is that as the saturation decreases, the tension goes up. And this is like a suction force, and sometimes this tension is expressed in terms of a head rather than as a pressure. And what it means is that as the degree of saturation or how much moisture is in the soil goes down, then the soil is more hungry for water. Remember that there is a negative charge on the outside of particles, clay especially. Look, clay is on the top here. And what we were saying when we were looking at the diagram of clay is that these clay particles are very small, and it's a little bit deceptive to be showing them, you know, as this big, and here's a sand grain that's that big, because in reality these clay particles are probably like 10,000 times smaller than sand grains. So they're way, way, way smaller than the sand grains. And because they're so much smaller and they have a really high surface area, and each of these surfaces of clay wants to be wet. it has an attractive force for water. The negative charge that's just inherent to a clay particle is always attracting water, and so what this diagram is showing is that clay particles will have a very high suction head when they're dry. As the degree of saturation decreases, then the suction head goes up. So, in other words, this is wet soil. Saturated means that all of the voids are full. And this is dry soil on this scale. So what do you think is the implication of the infiltration rate? I told you earlier that all of this is headed towards infiltration rate. We're trying to predict how quickly water can penetrate down into the soil. So when the soil is dry versus when the soil is wet, how does the infiltration rate change? What do you think, Tim? All right. It's closer to saturation. That means that the suction head is lower, that there's less tension, meaning that all of those grains are surrounded by water. They're happy. The negative charges that want to be exerted onto water are being exerted. And so the water infiltrates into the soil very slowly. Really, what accounts for infiltration when the soil is saturated is just the head of the water itself. Like if we have, here is a land surface, and if this is the water table underneath the land surface and it starts raining, then infiltration is going to be fast because we've got some of the soil here that isn't saturated. And so the soil essentially is sucking the water down through the void area. This is sometimes called the vadose zone, or it's called the unsaturated zone, or the zone of aeration. Has a couple of different names. But when the water table rises, when the water table's all the way up to the ground surface and there's puddles everywhere, then the water will infiltrate a little, but it will only infiltrate in as much as the water itself is moving underground sideways. Maybe there's a stream here and the water is infiltrating into the stream, this base flow movement. And so any infiltration that occurs here is just to replace the water that has bulk migrated away. And it's not because it's sucking down to sort of quench the thirst of the dry soil that was unsaturated initially. So during a storm, infiltration rate decreases. At the beginning of a storm, especially if it's been very dry, infiltration is quick because there is a really high soil water pressure. But then as the storm increases, the soil water pressure goes down, and so does the infiltration rate. The reason why I like this figure, it shows an experimental approach to trying to classify infiltration rate. And there are predictive models that, equations that use typical values for certain soil types, or you can go out into the field and you can find a soil that you're interested in and see how quickly does water actually infiltrate with a double-ringed infiltrometer. And it's a way of measuring. You put in it's basically a pan. You firmly seat the pan down in the water and in the soil. You pour in water and you watch the rate that the water decreases, or you keep a constant head on it. You keep pouring water in and you make sure that the depth is the same, but you keep track of what volume you're replacing, what's the flow rate in as the water infiltrates. But the reason why I like this figure is it shows the wetting front. And this is, you can see that even though we think of this, all below it is soil, unsaturated soil, but above it is saturated. And that's the reverse of what normally happens. Ordinarily, in sort of equilibrium conditions, we'll have, here's the water table, and so you'll go down underground, and this is the unsaturated zone, and this is saturated. And saturated means all the voids are full of water. Now, unsaturated doesn't mean there's no water in the soil there. It just means that some of the voids have air. Some of the void space is occupied with air. There's still some moisture in there, like coating the soil grains. It's tightly bound to the soil grains, but there are some air spaces in there. So in this figure, what it's showing is that during infiltration, whether it's an artificial test like this or an actual storm event, what happens is that there's a wetting front where this is saturated. You know, the water is passing through the soil. It's moving downward, but all of the grains are full of water. All of the void spaces are full of water as this wetting front moves downward through the soil. And so if it started to rain, here's the unsaturated zone, maybe after a few minutes, then all of that part would be saturated. And then a few more minutes, it's traveled down further, and then we'd have some saturated zone penetrating through the zone that's typically unsaturated. Yeah, well, as the storm occurs, but you know, it could be that there's a rock someplace. You know, it could be, you know, a dome-shaped rock, and there's soil underneath the dome-shaped rock, and so if the water is going down, then the air here would have no way to migrate out, because normally as the wetting front goes down, the air is basically just escaping out of the top of the soil, and the soil itself is breathing. But if there's soil underneath the rock, then that air would be trapped. So the case that you described, it would be trapped if it was a non-homogeneous soil. If it's soil with rocks and gravel and maybe a layer of clay. If the rest of it was sand, but you had a clay layer, and water moves very slowly through clay, and so does air. So that could be another case potentially. Okay, so here's some vocabulary that you need to learn. These are some words you need to memorize the definition to and be able to explain what they are. The process of infiltration is what this chapter is all about. Infiltration is precipitation minus runoff. You know, the amount of a storm that doesn't run off is that part that infiltrates. So really the way to think about it is runoff is precipitation minus infiltration. You know, the part of the storm that doesn't get down into the soil is the part that is going to run off. So infiltration is what it's all about in this chapter. Now, exfiltration is the evaporation of moisture from the soil into the atmosphere. And that's different from evapotranspiration. Evapotranspiration, which we talked very briefly about earlier in the semester, is the process of plants themselves exhaling moisture, or evaporation from a free surface of water. So evaporation from a lake might be lumped into evapotranspiration. But exfiltration is evaporation of moisture directly from the soil. If you had a soil that was being baked by the sun and it was evaporating on a dry day. Redistribution is just movement back and forth between the saturated zone and the unsaturated zone. This is water movement in the unsaturated zone, and so what we're talking about is this zone in which there are some voids in the soil. Capillary rise we've talked about already, and that's the idea that even above the water table, there's going to be more moisture in this part of the zone of aeration than if you go a little bit higher, there'd be less moisture, because as you get closer and closer to the water table, a greater fraction of those soil voids are full because of the the capillary effect. You think about the diagram that we had of the sand grains. Remember that in the capillary effect, if the tube gets bigger, then the water level goes down. But if you have a really small diameter tube, I'm going to try and draw that as carefully as I can to represent a small diameter tube. So in a small diameter tube, the water level can rise higher. So if you have some distribution of sand grain sizes, you can see that here's a really small void. What's the probability that you're going to have a small void and then above that, stacked above that, is also a really small void? And then above that is a really small void. Because what we're dealing with, we're saying that it's sort of like a little glass tube. All these very small interconnected voids are like a small diameter glass tube that the water level can rise up in. So there's like a distribution. You could have a cumulative distribution of the effective diameter and then this is the percent of soil. So if you want a really small effective diameter, maybe it goes down to here, a really small effective diameter is what would give you a really high capillary rise. But a very large effective diameter, most of the soil is going to have a large effective diameter and the capillary rise won't be as big. And so down here in the diagram of capillary rise, the soil that's very close to the water table is going to have more capillary rise water than if you go higher up. The probability of any particular soil void being connected to a bunch of soil voids beneath it with very small diameter voids, that's not very likely. And so the capillary rise affects mostly the zone that's close to the saturated section of the soil. You can see that here the plant is taking moisture in through the root structure. And then the other thing to take into consideration is interflow. And interflow is just the sideways movement of water in response to variation in the soil slope. And it's the movement towards some sink, like a stream or just maybe it's the interflow is moving towards a pump where groundwater is being discharged from the underground aquifer. So interflow is the sideways movement. It's the only one that was the bulk flow of the water sideways. Everything else is basically up and down. I guess the plant uptake they're showing here as a sideways thing, but really what the plant does is it just takes up the moisture that's very close to the soil grains around it. For the most part, there's a statistic out there that says over the entire Earth's surface, on average, the rainfall that falls onto the Earth rather than onto the oceans, 76% of the precipitation that falls onto land infiltrates. The infiltration is really important because it provides water for plants that are cultivated and also natural plants. And so people in agricultural engineering study infiltration very carefully, and one of the things that agricultural engineers try and do is find new ways to actively manage infiltration rates, and so that they're favorable for the crops that are being grown. This diagram shows the pressure head of water with respect to the degree of saturation. And it sort of shows what happens to water as it begins to drain and how you can drain it to certain degrees. And we start off with fully saturated soil, where all of the voids are full of water. Then that means that there's going to be a very small pressure head. You can see that the pressure head is essentially zero when the soil is fully saturated. If you have a fully saturated amount of water, let's say that we took from underground, here in the saturated zone, we took a cube of it, a three-dimensional cube of it, and we removed it. We basically, we took it out into the air, and what we're going to do now is we're going to allow it to drain by gravity. And so little drips of water are going to start coming out of that as it loses water. And you can see the range of moisture loss, and the field capacity is the amount of water that is in there that can be removed just from gravitational draining. And so if you extracted soil and it's not like you're heating it up and it's not like plants are trying to take the moisture out of it, it's just that it's strictly gravitational draining, the field capacity corresponds with how much water would be in there after that. And so if we think back about what's happening here, if there was no plant uptake, but it's just the precipitation event is over. The soil was fully saturated during a precipitation event when infiltration was occurring. That stops, then the moisture level is going to decrease to the field capacity. And you can see that there's a negative pressure head associated with that because the soil once again sort of becomes hungry for water. There's a propensity for it to want to be coated with water because of the attractive forces that it has. If plants are there taking water up, they can take out water even that gravity wouldn't have drained. And so the plant available water down to the permanent wilting point. And that's an interesting description for a soil property, permanent wilting point. And it's a little bit of a, it can throw you for a loop because it's not the soil itself is wilting. The soil has just lost a little bit more moisture. But what the permanent wilting point means is that the plant can take out a certain amount of moisture, but then it gets to the point where it can't draw enough moisture out of the plant to make up for the moisture that it's losing due to evaporation and transpiration. And so the plant itself wilts. And so this permanent wilting point that's indicated, that's kind of a highly variable thing depending on what the plant is and what the soil is. For all of these, the pressure heads are going to vary depending on whether it's a clay loam or a sandy loam and vice versa. This is just sort of a conceptual diagram showing these different divisions. And so the permanent wilting point is the point at which the plant that would be trying to take water out of the soil has died because it's not able to extract any more moisture to further its respiration. So that's how much water you can extract from the soil due to plants. And then the next limit, the hygroscopic water, is the amount of water that's forming very thin layers around the soil grains themselves. If the soil is warmed and some evaporation occurs from the soil, then the hygroscopic water is the amount of water that's just every surface is coated inside the soil, but the voids aren't. So let me draw a diagram of that. There's going to be these particles of soil that are all connected together, and you can see that there's voids here, but there can be water, a thin layer of water around every particle, and there can still be voids. In fact, there's quite a lot of voids here. You can see that there's a lot of areas that aren't full with water, even though the thin layer goes all the way around every particle. Now, once you get lower than that, that's considered unavailable water because there's such a tight bond between that last completely coated layer of water around soil grains down to the point where soil begins to be considered dry. Oven dry, if you heat it up to 104 degrees Celsius to oven dry it, or air dry at the ambient temperatures. That may vary based on what the ambient temperatures are for the environment in question, but it gives you an idea of the different zones that a drying soil goes through, and that the pressure increases, the suction pressure or the suction head increases as the drying gets further and further along. So the soil profile horizons, if we take a look at the pressure profile, which is what this curve is, the pressure is relatively low down here in the groundwater region because the soil grains are fully saturated. But then as you get further away from that water surface, you can see here's what's called the capillary fringe. That's the zone where water is being drawn up more than it would just with a typical moisture profile in the soil. That part of the reason why there's more moisture here in the capillary fringe is because of the capillary effect, and so the negative pressures are lower. Down here towards the top, there's a high pressure because there's the lowest amount of moisture. The sun is beating down on the soil here, so in the root zone, the soil is warmer than in the zones beneath it, and so that's going to mean it has less moisture. And since there's less moisture, the negative suction pressures are higher, or further to the left. There's a greater suction pressure. And so when it begins to rain, that really low pressure in the root zone means that it's going to suck the water down very quickly. And so it will move up to fully saturated, but then as that wetting front moves downward, it's not satisfying as negative a pressure as it was initially. And so the wetting front slows down because the suction pressure that it's being drawn by decreases during the storm event. So as infiltration occurs, you can see that it will cause the water table to rise in the area that there is infiltration. If it was just raining over here and not over the entire surface, then the water table is going to rise in one location, and then it's going to have the sideways movement of the water towards the lower water table elevation, ultimately towards an outlet. In addition to the soil condition, infiltration rate also depends on vegetative cover. The root structures that penetrate the soil can be an important conduit for moisture making it down into the soil. Water can move along the roots of the soil along the roots of a plant during a storm, sometimes much faster than it can travel through the voids themselves. The soil properties in the handout that I've given you for the homework assignment, there is a table 7.4.1 that shows a range of porosities, a range of effective porosities, wetting front, soil suction head, hydraulic conductivity, and then a typical value. On the homework assignment, what I tell you to do is just use the typical value, which is the value that's above the range that's given. So in the case of sand, for example, it's 0.374 through 0.5. Well, the typical value within that range would be 0.437 for a sand, and so on. And so the rate of infiltration depends on these soil properties that varies depending on what blend of clay, silt, and sand there is. And then it also depends on what kind of plants are on the cover and then their condition. A grass that's cropped very closely is going to have a different infiltration rate than long grass. And likewise, if the spottiness of the grass, sometimes there are patches of bare earth, sometimes the grass is fully and evenly covering an area. And there are tables for C value in the rational method and curve number and the SCS approach that we'll learn later in the semester that corresponds to different vegetative cover and different combinations of soil surface. I've already told you that the unsaturated zone has a couple of different names. Sometimes it's called the vadose zone or the zone of aeration. When it's referred to as the vadose zone, that phrase is used quite often in the terms of environmental engineering and hazardous waste cleanup, because there are some chemicals that will infiltrate underground. In addition to water, things like dry cleaning fluid can infiltrate, and for a lot of years it was common for chlorinated solvents like dry cleaning fluid just to be thrown into an open ditch, and then those solvents would start sinking down through the soil. And so sometimes those chemicals get stuck in the unsaturated or in the vadose zone. And if a chemical is in the zone of aeration, sometimes a treatment strategy they'd use to extract it would be just to ventilate the soil, to have pumps that are forcing air underground to try and air out the soil. And so if gasoline, for example, was in the unsaturated zone, we know that gasoline has a very high vapor pressure and it's prone to evaporating if ventilated. And so the ventilation of the vadose zone would be a good way of eliminating that kind of a pollutant. Unsaturated zone or zone of aeration would be the typical terminology that's used when we're studying infiltration, though, excluding the environmental kinds of things. If we break it up very broadly, the zone of saturation is where all the void spaces are full of water. The zone of aeration is where there is some air in the void spaces. And we can break the zone of aeration into different regions based on the effect of the surface in the root zone, where we know that the temperatures are going to be elevated and water is being taken up by the roots of plants. And also you're closer to the air surface, and so that may enhance evaporation of moisture from the surface in the soil water zone. The capillary zones down beneath, where there's a little bit more moisture than you'd see maybe just from gravity drainage because of capillary forces, and then the intermediate zone is just in between those two. When a storm begins, there is a very different distribution of where the precipitation is at different times during into the storm. And so this is showing along the x-axis when the storm begins at time 0 of a storm and after a long period of time. And if you draw a line, a vertical line at any point, what that will do is it will tell you how much of the moisture is where at a certain amount of time. So for example, in the early stages of a storm, at the very beginning, the water is just starting to infiltrate. A great fraction of the water is just starting to infiltrate. And so the infiltration rate, you can see, is decreasing over time. And more of the water will be in surface storage. So that means ponding in the surface, small puddles, shallow puddles. But then over time, that decreases as the surface storage, those puddles that are the surface, begin to infiltrate down into the soil. And so there's an increase in the soil moisture. And you can see the soil moisture, the fraction of water that is bound as soil moisture decreases over time as that wetting front goes from just an increased level of soil moisture and then it gets down into the saturated zone. So groundwater flow is the movement of water within the saturated zone towards an outlet. And there can even be sideways movement to the soil. Unsaturated flow is the sideways movement of moisture through the soil. Overland flow would be the fraction of, once you get to a certain point of precipitation, the precipitation is still happening, but infiltration rate decreased. Overland flow occurs when the precipitation rate's greater than the infiltration rate. And so overland flow is essentially runoff, the beginning stages of runoff. And channel flow is the movement of water through a distinct channel like a stream or a ditch of some sort. This is just an illustration of those 3 different zones that we were talking about before: soil water zone, intermediate zone, and capillary zone. This is zooming in sort of on the capillary effect a little bit more, and it's showing that at the water table, if you go below the water table, the soil moisture is fully saturated. And in fact, if you get up from the water table a little bit, and this is just sort of a schematic diagram, obviously if it was still fully saturated, then the water table would be starting here. What it's just showing is that if you have a lot of small voids, the water table is, the amount of water is going up because of the capillary effect, but then the percent saturation decreases until you get to the the typical moisture content of the soil. This is before rainfall starts and before infiltration begins. And the slope of that line can vary depending on if it's clay or sand, how quickly the zone of the capillary zone tapers off is a function of the soil type and the distribution of void sizes. Here's the definition of porosity. It's the volume of voids relative to the total volume of a soil. And you can see in this diagram that in a certain volume of soil, there is some places where it's air-filled voids, certain places that are solid particles of soil, and then there is a thin layer of water around these particles of soil. So in this case, the porosity is any place where the solid particles aren't. And the soil moisture content can never be higher than the porosity. There can never be more water in there than the porosity simply because the voids are where the water is able to occupy. So we consider saturated soil when the amount of water content is equal to the porosity, then that's 100% saturated. The initial water content is before a wetting event, and the saturated water content is after a wetting event. So the change during that storm event we can calculate by looking at what the initial moisture content was and what the final moisture content. And even if after you drain the soil, the amount of water that's bound there just due to the attractive forces between the soil and the water is the residual moisture content. So here's a formula for the effective saturation. And the effective saturation is how much water can be held by the soil that compared to how much can be drained out. Even when you drain the soil out with gravity, it's still going to have some moisture around the grains just because of the tight intermolecular forces between the water and then the force between the soil grain itself. Remember, a lot of the soil here is SiO2, silicon dioxide, and there's a strong polar effect between the silicon dioxide and the water, and so that's why there's a lot of residual moisture there. And here's the formula for the effective saturation that says how much water can be taken out after a storm event. Darcys Law explains the movement of water through saturated soil as a function of the head of the water, and there's an experiment that has a constant head between two reservoirs, and if you have a certain cross-sectional area of water that the soil, cross-sectional area of soil that water is passing through, Darcys Law says that the flow rate that you can get through a column of soil like this is partly a function of the cross-sectional area. It's the water head elevation divided by the length, and so this is a slope. And then K is the hydraulic conductivity of the soil. And when we get into the well equations later in the semester, Darcys Law is an important part of predicting how much flow can come out of an aquifer when a well is being used to pump fully saturated, out of the fully saturated zone. Sometimes we refer to the slope of the water head as this variable J, and Q is a flux. It's the flow per unit area, lowercase q. So Darcy's flux can be calculated as that. All right, so let's do an example here applying Darcys Law. If we have a fine sand with a hydraulic conductivity of 3 meters per day, then what would be the flow rate through a column that's 1 meter? Here we have a 1 meter long column, and it's 25 centimeter diameter, and the water that's in this tank relative to the water that's in this tank, the head differential is 35 millimeters. And so what's the flow rate Q that would pass through that column? So we'd expect 5.15 liters per day to pass through that column. And of course, if it was longer, if it was 2 meters long instead of 1 meter long, if we doubled the length, then from Darcy's law we can see that you would cut in half the flow rate of water through that column. Or if you had increased the cross-sectional area, if you doubled the cross-sectional area, then you double the flow rate that can pass through that column of soil. And so Darcy's law is a way of experimentally understanding how quickly water can pass through soil as a function of the pressure head that's applied there. And hydraulic conductivity is a key aspect of accurately predicting how quickly water flows through soil. When infiltration occurs, the wetting front moves downward through the soil. And initially, you can see that the initial distribution is that the water here is at its initial moisture content, but then as water ponds at the surface, then the wetting front moves down. And you can see that over time, a thicker column is more fully saturated, and that wetting front goes down over time, and then eventually the soil moisture curve rebounds to the original state. During infiltration, the moisture content is fully saturated at the surface, and what we do in the green amped model that we're going to be learning next time when we get together in class is we're going to be trying to simplify the actual wetting front with some assumption of a simplification of what the wetting front looks like. And in the green amped model, what we do is we, first of all, one of the important assumptions of this model that we're going to use to predict how quickly water can infiltrate, we assume that it's always ponding at top, that there's 100% of the time that instantly, as soon as the rainfall event begins, that there's pooling of water above the surface, meaning that there's more water available than can infiltrate. And then what green amped tries to do is tries to estimate how quickly the water is infiltrating by calculating the length of the wetting front, and it assumes that it's going from the initial moisture content to fully saturated just sort of instantly, rather than a gradual increase in moisture content as the precipitation slowly picks up. It assumes that the storm instantly caused ponding at the surface. And so we use Darcy's law and change it into this green amped model for trying to predict the infiltration rate. So that's just sort of a preview of what we'll be delving into in class on Tuesday. If you've got a computer, you can bring it. We're going to work an example using Excel in class on Tuesday. So let's take a look at these announcements before we finish for today. I've given you the homework assignment, and you can start thinking about that last question. I ask you to consider, what are you going to do after you graduate, because it's going to be here before you know it. You know, probably February or March is when you should start putting together your resume and sending it out to places. And if you're thinking about going to graduate school, you need to start making those applications now, actually. There are plenty of graduate schools that have January 1 as their application deadline, and earlier deadlines if you want financial aid. You know, there are some schools that want you to apply in October for admission next fall. So anyways, that's sort of the reason why I asked you that final question on the homework assignment, which is due on the 15th. So I'll see you on Tuesday. Have a great day.